In this page, we want to talk about relative entropy. Relative entropy is non-negative. Relative entropy is a Kullback label distance between two distributions, PZ and QZ. In this notation, the order which comes first matters. So basically, dP and Q is different from dQ and QP. So if we switch the order, the number changes, the result changes. And this is defined to be this formula right here. So Z is the dummy variable for the outcome of a random variable. So basically P of Z log P of Z over Q of Z. So that is the, so Z is the domain of the random variable, right? Or the range of the random variable, okay? So PZ, summation of Z, PZ log PZ over QZ. There's supposed to be a parentheses, closing parentheses at the end. Sorry about that. So there should be closing parentheses right there. And now suppose QZ and PZ are strict positive distributions, which means that at any point Z, there is no zero probability masses. Okay, all are positive. Okay, that SP and SQ denote their alphabets respectively. Okay, and then the negative relative entropy between P and Q is equal to this, according to the definition, PPZ, but since I have a negative sign right here, the inside the log argument has been inversed. So QZ over PZ. So that is negative relative entropy. This is upper bounded by log of average. Since log is a concave function, function of average is greater than average of function. So inequality goes this way. Function of average is greater than average of function for concave function, which is log. And then we cancel PZ and PZ right here. So this is a summation of a QZ over the set SP. So SP is the alphabet of distribution PZ. Okay, so this may not be equal to 1, right? Because this is only over SP. And then this is going to be upper bounded by log of this now, which is the whole alphabet, SQ. So SQ is the alphabet for the QZ. So this should be equal to 1. So this is 1. So log of 1 is 0. So negative relative entropy is upper bounded by 0. So relative entropy is lower bounded by 0. So does relative entropy between P and Q is greater than or equal to 0. Now we need to think about when we get equality. So in order to get equality, we need to get equalities in two places. First place right here, second place right here. So let's take a look at the first place. This is the average of function and then function of average. This is based on the Jensen's inequality. And the Jensen's inequality says the equality is met when this ratio is constant. So equality only PZ over QZ constant. Okay, so equality means that QZ over PZ is constant. Okay, so if it is constant, then this one right here is equal to some constant C, summation of this is a C, and that number is supposed to be smaller than or equal to 1, and then it is equal to 1 when the set SP is equal to SQ. So the alphabet for the two distributions should be the same if this is came out equal. So that means the second inequality, when the second equality holds, the second equality holds only if SP equal to SQ. So that means QZ is equal to PZ over SP. So in such a case, for every alphabet, QZ is equal to PZ. So the two distribution, QZ and PZ, should be the same. Okay, so in such a case, everything has been proved. Does relative entropy between P and Q is greater than or equal to 0 with the equality if and only if PZ is equal to QZ over all Z inside the alphabet SP. Okay, so the two distributions are the same. So this equality is easy to prove when PZ is equal to QZ. If PZ is equal to QZ for all Z, a little bit tricky when this is equal to 0, and then we need to show that PZ is equal to QZ for all Z, but as I have done in here, basically, when you set this equal to 0 in this inequality, both places, if it is equal to 0, then the two distribution must come out to be the same. I will have another way on pages 87 to prove this. Okay, now example on relative entropy. Let the alphabet to be equal to 0 and 1, 0 and 1, and the two distributions px, qx. So px when x is equal to 0 is 1 minus r, and when x is equal to 1, it is r. So r is a number between 0 and 1. And then q is 1 minus s and s. Okay, so the relative distance between, and relative entropy between P and Q is written this way according to the definition that is different from relative entropy Q and P, which is this. So when you switch the order, the relative entropy for the two cases are not the same in general. So relative entropy is not symmetric in general. But when you set R is equal to S, then obviously they are the same. When R is equal to half, S is equal to quarter, then dPQ is 0.2075 if you use the calculator. And then dQP is equal to 0.1887. Okay, that's the example on relative entropy.